Our second technique for finding parametrizations is to use special coordinate systems. There are a lot of shapes that look really nice in cylindrical coordinates or look really nice in spherical coordinates. And so we can very naturally use those. What we do is in those coordinate systems, we have formulas for what X, Y, and Z are. We can re-express our shape in terms of those coordinate systems. And then we do the same thing. We try and say, okay, how can I find one of my new coordinates as being a function of the other two and use that to parameterize my whole shape by plugging back in for X, Y, and Z. So it's a little bit easier to do if we do an example, so let's do that. So here, this formula, x squared plus y squared plus z squared is equal to 4. That's a formula for a sphere of radius 2 centered at the origin. And spheres, we could do this the same way we did it before by solving for one variable in terms of the other two. But if we do that, actually, we have to break it into two pieces because there's going to be a plus or minus in the square root. We're going to have two separate parametrizations, one that covers the top and one that covers the bottom. But if instead we do it in spherical coordinates, this equation here says that our radius, our distance from the origin, should be equal to 2. The other two variables are independent, theta and phi, and so we just have our rho variable equal to 2. So what we do is we then say, okay, here's our u and here's our v. Those are our two independent variables. And then I write down a parameterization by plugging in my formulas for spherical coordinates. Rho cos theta, cos sine phi, rho sine theta, sine phi, and rho cos phi, like so. I'm just taking my formulas for spherical coordinates and I'm plugging in rho equals 2, and then my independent variables theta and phi are equal to u and v. And that gives me a parameterization of the sphere. And here I have to know what numbers am I allowed to use here. Here, I'm going to use theta. Theta is a variable that's supposed to go between 0 and 2 pi. I'm supposed to start between angles 0 and 2 pi. So my first independent variable should go between 0 and 2 pi. And my second independent variable, because it's the latitude coordinate, is supposed to go between 0 and pi. It starts at the North Pole at 0 and ends at the South Pole at pi. Another example is this cone shape. X squared plus y squared is equal to z squared, where 2 is greater than or equal to z is greater than or equal to 0. So this describes a cone inside three-dimensional space. We could do this by solving for z in terms of x and y, and that would be perfectly fine. But we could also use cylindrical coordinates. If I plug in cylindrical coordinates, this becomes z squared is equal to r squared, and z is greater than or equal to 0. And we can simplify that. We can say that r is equal to z. So that solves for r in terms of z. R becomes our dependent variable, and theta and z become our independent variables. So let's say that our first independent variable is u and our second independent variable is v, and then we plug back in r times cos of theta, r times sine of theta, comma z. Our formulas for cylindrical coordinates, we plug in these formulas that we got. So here, once again, we have to describe what exact region of integration we're working over. Our u coordinate is supposed to go between 0 and 2 pi, because that's an angle coordinate, and our v variable is supposed to go between 0 and 2, because that's the region that z went through. So that's an example of parameterizing a cone using cylindrical coordinates. We could also have done it the regular way. We could also have done it using spherical coordinates. All those would be perfectly valid ways to find this to find a parameterization, but this is one that happens to work, and the resulting formulas are not too bad. So this is just all getting at the fact that there's not always an obvious choice, and some parameterizations might be a little bit easier than others. You know, the fewer trig functions you have inside there, the fewer square roots you have inside there. We are doing calculus, and those kinds of things are going to make our lives more difficult sometimes. So be aware that just because you can use a particular coordinate system doesn't mean it's necessarily the most straightforward choice.